Hello everyone and welcome into yet another live stream, and what a perfect timing it is. Oh, great. I've been waiting. There's some construction work happening outside my apartment, and because of that, every now and then you're gonna hear an occasional drill or whatnot. It gets surprisingly loud at times. I know. It seems like I'm just positioned in the worst possible spot from what it would seem like. The acoustics are just really not helping me. How have you been? Hi, Checkup, by the way. I've been good. I've been good. I've been decent. The most recent video I uploaded just went past, just got past 10k, which is pretty neat. It's the second video to ever do that sort of thing. I can see it's 10k, which is the second most popular video on the channel. This is really good. This is really good. I honestly thought it would feel more fulfilling, but in comparison to the additional quantum mechanics, it's still nothing. Like, it just got to 10k, and it's still one digit lower than addition to quantum mechanics. So, I mean, I am glad that it's blowing up. It's really nice. A lot of people seem to be really enjoying this video because it explains bonding pretty well. Well, it explains bonding period, you know, just like one of the only cases in which bonding is explained. You are seriously so underrated. I wouldn't say that. I would just say that this video set different standards for myself, and I kind of psychologically haven't really gone past that yet. Hold on, what was I saying? Oh yeah, there's construction work happening right outside, which is perfect timing, because today we're actually going to record all of this. All of this. That's actually what I should start with. I should start with, first of all, actually, setting up the free animation. Hold on. And then recording all of this. Give me a second. I need to take a huge sip before recording because there's a lot to record. I need to get into my hypomanic time to record state. How are you doing, Kanika? I'm sorry for asking, I'm still trying to get into the streamer's mood. Why do I like coffee so much, make it? It brings me into my hypomanic state. What is energy? No, sir. Hi there, guy. Hi. Welcome. I'm doing great. That's a lot of exclamation mark. That's either really great or rewarding. But you know what? I'm an optimist. I'm going for really great. I'm so happy for you. Hi, the lamppost. Hi there. How you doing? I think 11D is where we were at last time. Correct? Boy, that's bright. Oh yeah, that's totally where we ended up. Okay. I should play some music, although I will go straight to the recording in a second. So electrons are exact same thing as kinetic again, just movement of something. In this case, movement of electrons is a bit different because all these electrons are negatively charged. So the way I would like to do this one is as a loop. So this will be the start of a loop at 3850, like this, with location and rotation. Also might as well save as a copy and delete all of the unnecessary alpha things, which are just going to slow everything down for absolutely no reason. There we go. Now we can move this way. Ah, damn it, it's all rotated by... Also in the video I actually want to make a bit because this grid is misaligned ever so slightly. So what we're actually going to do is we're actually going to align this. So we're going to yeah, for all of these, add a keyframe, and then we're going to reset everything. There, now they're no longer misaligned. Why are you staying there? No. Okay, the grid is already in the center. There we go. No, that's love. Just did 120 shin hits on the wall corner. Why? Hi there, Ashwin. I'm doing better, so it's great. What are you asking me? I feel cared for. Well, I'm just honestly glad that you're doing fine. Y'all don't understand just how worried I get when y'all are not doing fine. Lamppost being a prime example of that, with the 120 shin hits. But it's honestly pretty selfish of all of you to not be doing fine. I feel like y'all should take better care of yourself. What was I? This 7, 8, 58. There we go. And now we're just going to record everything. How festive. Right, you have the premiere, and this is where the project will go. You finally win it without single one. You're so selfish. I don't know why. I am selfish. That is true. That is absolutely true. I am not gonna contend with that fact. I'm not gonna contend with that fact that doesn't care about my feelings. There. That's why I start my sequences, but just by dropping a random image in there. What's Making doing here? Like an animation or something? A video, a full-blown video. This is a video which we've been working on live streams. And we've actually finished the entire script for that video. Originally it was going to be about thermodynamics, but it slowly pivoted towards energy and what is energy. And so that's what we end up with. Hold on, I'm going to do something which might be pretty loud. Really loud. You know what? I'm just gonna mute myself on OBS. Not tell. There we go. Yeah, so the thing I did is I just simply is walking sick. You should hear me way better now. That's because I switched from my mixer to my basic setup. So now my voice is different. It should be higher in quality actually. And that's because this is the one we'll be using to record the video. That's because if I click the record button, and I do 1, 2, 3, 1, 2, 3. Hello everyone, welcome into yet another video about energy, quantum mechanics, physics, chemistry, or whatever of the sort. I don't actually know exactly. And 1, 2, 3, 1, 2, 3. Hello everyone, welcome into yet another video about energy, quantum mechanics, physics, chemistry, or whatever of the sort. Right away, let's fix it. Exactly. Because it's unbearable. 1, 2, 3, 1, 2. bit too loud. 2, 3. Hello everyone, welcome into Yena. Sick. That's why the name of this live stream is, you know, perfect timing, because there's a construction crew right outside my window. So, you know, I'm gonna have to re-record a lot of things because they are really loud. So. We do be energying. We do be energying indeed. What is energy? Yep. Capacity for doing war. You were talking through a mixer? Yeah, the entire time. I was mixing myself. That's why the audio was so awful, because you're meant to blend, you know, like foods and veggies in it, not really audio. And that's me. Energy and walk are, I guess, similar. They are actually practically the same thing. Since, I mean, their equation in classical mechanics are the same. It's force over displacement. That's both for walk and energy, because energy is capacity for walk. Walk is just energy use. Yeah, that's basically what I'm trying to tackle in this video. The fact that, you know, when it comes to definition of energy, you have energy, which is defined as the capacity for walk, and walk is basically defined as you know, usage of energy. It's a very circular definition. It's a mixed user for microphone, feel offended. Okay, now we got that out of the way, let's record the thing. Now that we try and test it, and it's clearly working. Light, heat, charge, movement. No, that's bloody awful. Light, heat, charge, movement. All of these things are completely different, and yet we use a single term called energy to describe them all. Why is that? Why would they be connected at all? And most importantly, what even is energy? Yeah, that's what the whole, like, first 30 minutes of the live stream will look like. We're 15 minutes in, it's gonna take longer than 15 minutes to record. Okay, there we go. Next one, kinds of energy. So first things first, what is energy? Well, energy is hard to define, but we all have a pretty good feel for what it is. So for now we can say that it's just the capacity for doing work and a conserved quantity. So if we had a ball, for example, moving forward and hits another ball, all of this energy will get transferred. That's kinetic energy, and it basically means movement times mass. Since energy is conserved, there isn't actually a way for us to lose this energy, and that's why it got transferred when our balls hit, because energy can't just disappear. Another kind of energy is potential. So if we take our ball again and move it up this time, the gravity wants to pull it down. We call it potential because there isn't really any physical representation for it. I mean, the ball isn't heavier, isn't glowing, isn't moving faster or at all, in fact. It's just there, chilling. But if we let it go, it falls. That's potential energy. It doesn't always have to be height. Potential just means potential to release energy. Technically, it isn't quite like the rest of energies because of the whole non-physical presentation part, but if you were to graph the amount of kinetic energy our ball has, you would see that it's disappearing. And then when we release the ball, the energy is reappearing. But this doesn't actually track our definition, since we said energy can neither be created nor destroyed. It's a conserved quantity. So that's why we made up potential energy. We just say that instead of our kinetic energy disappearing and reappearing, it's getting converted into potential energy. So if we add another line, summing both energies together, it will always stay constant. Which means that the more energy we, in quotes, lose right here, the more we'll gain right here. So the lower this drops, the higher this gets. I love the voice. Yeah, that's the benefit of having a decent mic. My voice isn't actually all that great. We don't know what energy is. We just know energy exists. We don't actually know energy exists. We made up the concept of energy. Hey, Meg, what's your nationality? You mean what country I live in? I'm not really much of a national person. I'm more of a dirty globalist myself. And I do consider the concept of nations quite silly. Indian. How old are you? That's a really good question. I'm Indian, 15 years old. Technically, I'm as old as this universe. Well, I guess, yeah. Fair point. Make it as an amazing script. Thank you. I walked on stream on this. Ashwin, I think you should not share your age without knowing people. Why is that? It's age. It's not like a it's not showing like its credit card information. What's wrong with sharing your age? That's such a mild thing. Ah, damn, coffee is phenomenal. I feel like at this point it's more of a placebo effect, where if I just taste it, I'm feeling more energized. I mean, the caffeine certainly does help too, but the placebo plays an important part. And so let's just recap for a second. This red line right here represents our kinetic energy, so the movement of the mass of the ball. Kind of like velocity. Actually, in this case it will be proportional to velocity. And the blue line represents the potential energy. In this case, the energy that can be released by gravity, so the height. Got it? Red line is the velocity, blue line is the height. I'll let this animation go in the background for a second to get the thing. Alright, now both of them summed up give us the total energy, which is always constant. Except it isn't. And based on what I described, it really seems weird. I mean, in what possible scenario would this line not be constant? No, really, this is a genuine question. Pause for a second and see if you can answer it. There. Got it? Well, the answer is pretty simple. And the animation was a bit of a hint itself, because at the end of it, our ball is stationary and on the floor, which means that both its kinetic and potential energy is zero. So our total energy of the ball is also zero. So what happened to the energy? Well, it got transferred to the ground, and that's where we find the actual constantness of our energy, and that is the total energy of our system, the green line, which would be the energy of the ball plus the energy of the ground, so this. This is the line which will always be constant, and that's why sometimes you'll hear insulated system in physics. What insulated system basically means is a system in which the total energy stays constant. But hold on, I just said that the ground here has some energy, but what kind of energy? It's certainly not kinetic, since it's not moving, and obviously not gravitational potential, since there is no place for it to fall. It's the ground, it's on the ground, so what energy did this ball movement turn to? I'm almost 5'11", 80 kilograms. I can beat up more people, not trying to flex. I know a few cases of age fishing. I don't know. I'm too much on. I don't age fishing. How does age fishing work? That doesn't matter. Okay. Because reading it, yeah, them's the lines. Right now we're going to thermal. You can just listen. This sort of live stream is a very nice podcast, I would say. Mushroom Economics Boxer. And you know what? I couldn't beat up any of y'all because I don't walk out, nor am I strong, nor do I know any martial arts. I'm just not beating people up. I'm more of a wholesome conflict resolution kind of guy, not really the get fists ready kind of guy. What topic you on? And thermal energy. Yeah. Hey, make it high, God Slayer. Okay. Ball movement 10 to. Well, this energy turned into thermal energy. What is thermal energy? Well, thermal energy is just the average movement. Well, thermal energy is just the average movement of molecules. Now, to that, you might say, hold on now, make it. Wouldn't that just be kinetic energy? I mean, it sure seems like if we move one of the molecules, it's kinetic energy. So when we move all of them, shouldn't it also be kinetic? And the answer is yes. Yes, it is. We just differentiate between them because it's a bit useful, but temperature is just the average movement at molecular scale. We'll get to why it's different than kinetic soon, but let's leave that for the thermodynamics chapter. Oh my goodness, there's no thermodynamics chapter. But let's leave that for later. Next kind of energy is radiant. I just realized that we completely switched the video and whoops. Radiant means electromagnetic waves, so light. When it comes to light, it's different. So far, both kinetic and thermal energy just mean the movement of stuff, so mass times velocity times velocity. But with light, it's different. Its velocity is constant, so c, and it has no mass. So what is its energy equal to? And that is a phenomenal question with actually a rather simple answer. You see, and right here is gonna be a sharp cut in the whole addition to quantum mechanics video. Okay, so basically, photons, so light, are kind of a particle and kind of a wave. So the energy would actually be proportional to its wavelength. That's where we get the light spectrum from. And something not many people realize about the light spectrum is that it's measured in meters. So its wavelength is really just the length of a wave. It's just length. Which means that a wave with length of 10 picometers would be gamma rays, and a wave with length of 100 meters would be radio waves. It's really just length in meters. So the longer the wavelength, the lower the energy. So this photon has a lot of energy, and this one, not a lot. That's radiant energy. But photons aren't the only elementary particles that can act as energy carriers. There's also... I don't actually like this line all that much because, well, you can use any elementary particle as... Wait, did I say charge carriers or... Hold on. Energy carriers. I mean, any elementary particle can be used as energy carrier. Hold on. Let me just double check. Electromagnetic radiation, right? Electromagnetic gravitational radiation. Oh, hot take. Maybe I learned boxing for self-defense and to teach my sister self-defense. That's fair. Thermodynamics, such a love and hate relationship with it. I mean, isn't thermodynamics just like statistical physics? Is that all it is? It's just basically using statistics to do physics. Damn views tall. Ah, yes. Fucking. Hello, what are we talking about? It's energy. We're recording the video for the energy video. Measurement vendors use X-ray guns. Is that a real thing? Seems. And why just not guns? Make it. Is the string theory unprovable? I don't think so. I don't know string theory. I haven't gotten that bit of physics yet. I'm barely dipping my toes in quantum mechanics. Like the relativistic quantum mechanics. We've been trying to get into relativistic quantum mechanics like a week ago. I'm not yet on the string theory level. We are talking about electromagnetic waves. Where? I'm just recording the script of the video. Oh, that would be a good video idea. Damn it. Oh, you just gave me a really good video idea, which now I kind of also want to do. But oh, this would be such a pain to do. Oh, this would be such a good idea. Oh, damn it. So basically, what's advanced physics actually about? And going from basic classical mechanics through thermodynamics, then quantum mechanics, then going into relativistic quantum mechanics, and then probably string theory, and then bleeding edge. Ah, that would be such a fun video to make, wouldn't it? Just going through each level of advancement. Tempting, we'll see. Alright. Bleeding edge was that? Bleeding edge is like the newest kind of science, basically. So in this case, bleeding edge would mean just looking up at some kind of paper, or going for like a Nobel Prize winner, something like that, and just taking the paper and then making a segment about the paper. Make it add particle physics in that too. What do you mean particle physics? Particle physics. Particle physics. Elementary. I don't know, where would I put it though? Because technically it's, I would say, about the same complexity as relativistic quantum mechanics. But like, well, the string theory, I guess, can count as this, but more than you think. I had to look up what particle physics in this. I really like this page because like you can press on different things and they will actually take you to those particles, and I just think that web design is great. This is an idea which we might actually do before Electrons Revisited. I feel like we're just swapping videos. When you're streaming DLC, I don't know, we have videos to make first. Cosmic rays. Make it on the grind, precisely. I mean, it clears so many doubts and creates 10 times more, but still, you should study that sometime, because it's an amazing part of quantum theory. Particle physics. I just don't really understand exactly what it would be about. It really feels like it's just elementary particles. It feels like chemistry of quantum mechanics. It feels like quantum chemistry, but like a, you know, small scale quantum chemistry. There are particles and there's spins. Oh, I love the spins of particles. You already know my opinion on the spin of particles. You already know how much I love it. There's a good TEDx video if you want an introduction. I'm not really much of a TEDx guy. I could check it. Electric, okay. Electric, so electrons, and with electrons it's the exact same thing as kinetic. Again, just movement of something, in this case electrons. But with electricity it's a bit different, because all those electrons are negatively charged, so they repel each other, which is different from standard matter, which comes together due to gravity. But that's kind of it, and I've already made too many videos about electricity and electrons, so let's move on to the last one, which is... looks like that. I mean, the thing is, when I look at particle physics, you can see there aren't all that many equations, which from a physical perspective feels like a huge red flag. That smells like chemistry. Hold on. Physicists love their equations. They would never create a theory, like, they would never create like a field, or I think there's a field with no equations behind it. There is no way. Wait, no. Derive from derivative. Yes, this one. Oh, to be fair, there isn't much math on this one either. Maybe I'm wrong. Huh. Why does Wikipedia just include... Why does Wikipedia just include random partial derivatives in thermodynamics, but they don't include any math for relativity? Cool. Then to use probability thingies. I already know how to use probability thingies. Wait, aren't you just describing quantum mechanics? Wouldn't have you did video on statistical mechanics as a precursor to quantum mechanics? No, I have not, but this video would work pretty well for that, I would say. And chemical. Hold on, let me sit upright. There we go. How's this already 8 minutes? And chemical energy basically just means the bonds. So carbon dioxide, for example, carbon dioxide molecule has it. That was awful. And chemical energy, which basically just means the bond. So carbon dioxide, for example. Carbon dioxide molecule has a single carbon atom and 2 oxygen atoms bonded together. But what is keeping them bonded together? What force is holding them close and not allowing them to drift? Well, this is a bit counterintuitive, because there is no force actually keeping them together. Instead, you need energy to break them apart. Imagine it like this. If you have a ball floating in space, here, imagine like this. If you have a ball... Imagine like this. You have a ball floating in space. Here, I'll just add an axis for reference. Now, if someone were to ask you a question, what is keeping this ball in place, how would you answer? Well, you'd probably say no force, because there really isn't anything holding it in place. Instead, you need force to move it. And that's what's happening with our bonded atoms. There's nothing really holding them together. It's just that you need energy to break them apart. And with that explanation, we can finally get to switching energy, like... ... Actually, for chemical for chemical energy, I guess I could have expanded a bit, but to be fair, I did just make a video on that topic. And it passed 10,000 views. It's good. This one. I mean, this is basically chemical energy. Well, at least the last chapter is. I mean, it's not that much. Yeah, it's just a nice concept to understand categorization of the elementary particles. Yeah, but in this case, what I want to do is I want to like showcase. What I would like to do is I would like to showcase how the toughness increases. Like, what would a tougher field actually mean? Because a lot of people know, or at least a lot of people think, that quantum mechanics is difficult without actually understanding why it's difficult. And so, you know, the interesting parts of the particle theory would just lose the message. My opinion on that video: change the damn title to "Why Isn't Water Explosive?" Lamppost, why? Okay, okay, fine. I'll showcase to you graphically why changing title of that video to "Why Isn't Water Explosive" is a bad idea. Electrons. In red, you have all of the video, the entire segment of the video that's talking about water and why it's not flammable. And in yellow, you have the entire portion of the video talking about electrons, with nothing to do with water. What do you mean? All physics is interesting, but I might be biased. I mean, yeah. Watch the video electrons before coming here. Well, what a coincidence. Alex, I have a question for you. As, you know, the smart guy who knows everything about physics and stuff. I have a video idea, and I'm gonna need you to review it for me, because I might do it right after finishing the energy video. Yeah. Alright. What do you think about the video? Basically going from the easiest kind of physics to the most advanced. Bleeding edge would basically mean I'll probably just go over like a Nobel Prize winner. And basically, in order to showcase what tougher physics actually looks like. Because, you know, a lot of people think of quantum mechanics as tough without actually understanding why is it tough at times. And that comes kind of in the way. Physics iceberg. Yes, physics iceberg of this. That's actually, yeah. That actually perfect summary. Yeah, but all kinds of stuff, I believe, ends up being used. Water topics, which is the main thing here. What I mean is. Lamppost. Ouch. Did you just say that everything I talk about when it goes to electrons is just getting used at the end for water? The whole point was to explain bonding. All of it. That's... Original slash not enough title. You mean the water one? You mean the iceberg one? For this one, I won't use an iceberg. For this one, I'll just use what's advanced physics actually about. This is fun because this I know, this is gonna be a new one for me, but probably doable. I have no idea how for string theory, I'll have to do a very basic explanation, and bleeding edge is, I'm just gonna do a single, like a 6-hour long live stream, trying to decipher at least a small segment of a Nobel Prize winner. Because, well, the whole point of bleeding edge will be that I can't understand it. That will be the point. I'll try to summarize something without fully understanding, and I'll be like, in the video, I'll say that I can't understand it because I'm not a freaking physics expert. Definitely a nice idea. Imagine it will be a lot of work, but giving a more or less a complete view in a single video could be nice. Yeah, I mean, the thing is, basic classical mechanics, well, that's a no-brainer. I'm going to have my element string theory too, so yeah, but you know, it's towards the end, so No one cares. The thing is, I've never researched string theory, so it's gonna be a fun experience. The thing is, what I'm mostly excited about is quantum mechanics. I know decently well, but well, I guess this is just quantum mechanics. In here, I just mean the basic quantum mechanics. I guess I should, like... Relativistic will be fun, because relativistic is... The difference between basic quantum mechanics and relativistic quantum mechanics is like a perfect example of what actually makes physics difficult / advanced. And I absolutely love it. String theory I'm mostly just curious about, but I'm not going to research a topic this deep for no reason. I need to make a video if I'm gonna research it. Free will, the illusion of free will. What does it matter? I love it how really often people debate. I already made theory. I love it how so often people debate whenever free will is real or if it's just an illusion of free will without ever defining free will. Listen, I'm all for debating if whenever free will is real or not. Just, we need a concrete definition first. Right, where did we finish off? Was it electrical or chemical? Oh, chemical, because I was just complaining about I didn't do it justice by the video about the electrons. Free will requires subscription, which you can get from the link in the description, https://megadabbis/ I mean, patreon.com/ I mean, youtube.com/ I mean... Goes over every single link. Okay, transitioning between them. Electrons to chemical. I don't remember these segments all that much. I can't remember the conclusion. How are we already on 9 minutes? Like 2 minutes of it will be wasted, so we're at around 7 minutes deep in the video. That's really deep. I was full on expecting this video to be 10 minutes long. Electrolysis, so turning electrical energy to chemical energy. And this one is pretty simple. That's just water. Or rather, what we can do with water. You see, water is made of 1 oxygen and 2 hydrogens, bonded like this. Now, what is the reason for the bond? Well, molecular orbital theory. Okay, it sounds awful, but you have to trust me. It's way simpler and more useful than it seems. Let's start simple with how we divide electrons. We divide them into shells and subshells, and we do it for some boring quantum mechanics reasons. Let's start simple with how we divide electrons. We divide them into shells and subshells. We do it for some boring quantum mechanical reasons, which we won't really get into right now because they are irrelevant. But here are the 2 most important things. First of all, energy. Hey, that's what this video is about. Here you can see these shells and subshells ordered by their energy. So the higher the electron is, the higher its energy. And because, as I mentioned, things don't really like having energy, electrons start filling these shells from the bottom up. Then the next thing is orbitals. So how many electrons can we fit on each rectangle? Well, we can divide those rectangles into squares which are called orbitals, and each one can fit only 2 electrons. There. Orbital theory. Now to add the molecular with water. So why are atoms in water together? Why are they there? Well, it's because when 2 orbitals come together to form a bond, what they actually do is they form 2 new orbitals. 2 bonding orbitals, and the bonding orbital and the anti-bonding orbital. Because of some quantum mechanical... The bonding orbital and the anti-bonding orbital. Because of some quantum mechanical Maffei function magic, which I explained in another video. Now the whole idea looks like this. The bonding orbital has less energy, and the anti-bonding orbital has more. Now the whole idea will look like this. When our hydrogen... Wait, did I just repeat myself? Yeah. When our hydrogen and oxygen bond together, their electrons move down from their orbitals to their bonding orbitals, releasing this difference in energy in the process, and they stay bonded. In order to break the bonding, you need to pull these electrons back to their original orbitals, which means bringing energy in. That's why if we have water, for example, and we'd like to turn it to hydrogen and oxygen, we need to bring in additional energy. So first what we do is we pull these electrons out, destabilizing the bond between hydrogen and oxygen and keeping them separate. Now what's the bond between two oxygen? Now once the bond between two oxygens is high, it's still lower than oxygens being by themselves, so they bond to reduce their energy as much as possible. Now what we do is we introduce these 4 electrons back, allowing the hydrogens to bond into a gas. Now that we have this higher energy hydrogen, we can turn it back into water to release this energy in the form of the explosion. Release this energy in the form of fire. Or in other words, we can turn electrical energy, movement of electrons, into chemical energy, unstable bonds, which we can then turn to kinetic energy, explosion and thermal. So there, we can easily switch between different energies, and these energies cannot be destroyed nor created. Except... Like, I'm not really contributing much to the conversation. I mean, neither am I. I was just recording in the background. Make it do your work. That's what I'm doing. Chill. Yeah, electrons, you would understand better with particle physics. What would I understand better with particle physics, though? The spin? I am actively avoiding spin. Look at what if these are right to get to diatomic molecules. Oh, I know if you saw that. I don't know if you were here for this section when I replaced one video with this video, but I was going to make a sequel to the electron video, where I would just add more stuff which I omitted, because there are so many things which I omitted for that video. And also I would like to get to large molecules. Carbon monoxide gave me trying to understand how it works. Maybe you should add a few jokes in that script to sprinkle it. Yep, forcing jokes in is not great. It's not a great idea to make a video funny. Yeah, right. Maybe if you avoid spin, the spin would avoid spinning in one spin either way, but it will spin. I know, I've already been over this with Flame. It's my Vietnam. There is a problem, because you see, if we draw a full diagram for this, we can see that we can use the explosion to power a generator to move the electrons, and then the cycle is fully complete. If not for the loss of energy. Loss of energy? I thought energy couldn't be destroyed nor created. And yeah, it can't. But the energy lost... And yeah, it can't. But the energy lost isn't really a loss of energy. It's energy lost as temperature. Our machinery gets hot and the thermal energy leaks away. But why would we consider thermal energy as lost? Well, it's because temperature is the ash of energy. And here's where we introduce entropy. So what is entropy? Well, entropy tells us how much useless energy is there. Okay, that's cool, but what is useless energy? Well, imagine a hot cube, like really hot, scalding hot. Then imagine placing an engine on top of it, which turns heat into electricity. Now, after placing this engine, we get electricity and we can use it to do work. In this case, I don't mean the human abstract kind of work, I mean the physical unit of work. Now, what's really interesting is that for thermal energy, when we use it in engines, we don't really actually care about how hot something is, only about how hot it is in relation to other things, like the engine, for example. Now, why is that important? Well, it's because if we go back to the ball and give it a velocity of 5 meters per second to the right, then congrats, it has kinetic energy. But if we give everything velocity of 5 meters to the right, then it still has the energy, but so does everything else. And now there is no work that can be done with that energy. That's entropy. So basically just useless energy. Energy which has no effect. Energy which, due to its circumstances, just can't achieve any work. We really often like to think of entropy as mixing stuff together, and there is a reason for it. It's because when you mix stuff together, it takes less energy to mix stuff than it takes to pull them apart. But the energy stays constant, which means that it takes less useful energy to mix than to pull them apart. And whilst energy is the theoretical measure of work you can do, entropy tells you the difference between the practical amount of work you can do and the theoretical one. Is that clear? Smart? Alright, good enough. Well, I hope so, because this explains pretty well why thermal energy is worthless most of the time. You see, high thermal energy means that these molecules have a lot of kinetic energy, but since it's thermal, they are moving randomly, which means it's difficult to harness this energy in any meaningful way. That's why we differentiate between them. It's because whilst both thermal and kinetic energies describe movement, this movement is much easier to use than this movement. Hence, this is useful, and this, most of the time, is just a loss. Okay, so that's why we differentiate between thermal and kinetic. How about electrical? He's assuming, yeah, I am. Real brain on the spin. This time make the video an hour long. I'm actually gonna be really surprised this video will end up being even 20 minutes long. But apparently it looks pretty decent. There's a pretty solid loss of how much I record in relation to how much there will be left in the end, because I will cut a fair bit of it, but only 5 people. It has like 20k subs. Oh, that's actually pretty average for my live streams. For my live streams, we usually oscillate between 5 and 12. Like, if there are 12 people watching, then it's a good stream. Okay. What are energies truly? Next one. How about electrical? Yes. Well, if you think about this, kinetic and electrical also seem like the same thing. Kinetic is just the movement of something, and electrical is just the movement of electrons. So why do we differentiate between those two? Well, it's because it's useful. If we differentiate between them, we can apply different equations, different models, and have the whole thing be more accurate. That's why when dealing with kinetic energy, the equations would look like this most of the time, and with electrical, like this. So yeah, the line between thermal, kinetic, and electrical is blurry, and we mostly just differentiate between them for the sake of convenience, unlike with kinetic, chemical, radial, and potential, which are very clearly different. That's because whilst kinetic is movement, chemical is based on the configuration of the electron cloud. Radial is based on the frequency of the electromagnetic radiation. And potential is... Wait, what is potential energy? Well, potential energy is hard to define. I mean, for radiant it's relatively simple, measure the frequency and with a bit of an asterisk, that's the energy, but potential is different. See, potential means stuff like gravity or charge or phase, I guess. That would be chemical, actually. It's slippery and it feels like it has a lot of components. Why is that? Well, that's because it's easy to pretend that whilst the line between kinetic, thermal, and electrical is blurry, it's well defined between the rest, but the truth is, it isn't. You see, energy is just a bit of a fiction. It's not really quite as simple as... And it's not really quite as real as we like to imagine. I mean, the concept is real and mathematically it makes sense, but it's not like a physical thing. Energy is just the potential to do work, which means that, in a sense, all energies are potential energies. So the true divide would look like this. We have kinetic energy, thermal energy, and radiant energy. Kinetic is for all of the equations of movement involving mass, and radiant is for equations of movement not involving mass. Thermal is for all equations involving movement with no direction. And that's it for movement energies. If we zoom out, we have the potential energies. So all the energies which are too specific, too complex, and are just too vast to fully describe, mostly dependent on position. But there are a couple for which we do have some models. Like for example, gravity, so position in relation to mass. Charge, so position in relation to electrical field. And chemical, so position of electrons. There's my alarm going. Now what's important to remember is that all of them are just potential energy, because it's just the potential for work. It's just that right here we have the potential energy based on movement, and right here based on position. And right here it's the mess we haven't described yet, or don't know, or don't have two concrete models for, or just straight up haven't discovered. So there, that's the energy. And speaking of segues, what are these models actually like? I'm actually kind of upset because I don't want to repeat myself in the video, but right here would be a perfect moment to insert the segue about how like potential energy is misnomer, because static energy would be a much better name, since all energy is potential to work. So well, it's kind of potential, but I have that later on in the video. Potential is like the energy gained the configuration of the system. Yeah, that's why I think static energy is a better name, because it basically potential is all the energy you have not due to movement. Potential kind of depends on the reference level. Everything depends on the reference level. So is kinetic. Oh, does it actually? I'm not a physicist. I'm just making video about physics. Okay, thermodynamics, quantum mechanics, classical mechanics, and the function. Right, this is the fun chapter, because over here we're going over all of the equations and we like sort of kind of semi-derive them. What are these models actually like? Yeah, shut up, pass make it. I don't care. So let's start with force. I won't get... really fucked up. So let's start with force. I won't overcomplicate it too much. If you have an object with mass m and you push it, then the stronger you push it, the more it accelerates. You can describe the strength of a push as F, and that's the force, well known as the equation of F is equal to ma. In order to truly understand what this means, let's break it down a bit. What is acceleration truly? Well, acceleration is just change in velocity in relation to time. What is velocity? Well, velocity is just change in position in relation to time. What is position? We're not doing this bit. No, I'm not doing a self-referential. We don't have to do this bit because position can be described with base SI unit, a meter, which means that we can describe velocity as meters per second, and acceleration as meters per second. Now to this we add mass, which also has a base SI unit of kilograms, and there. Now we can describe the force in relation to just base SI units. And what I like to do now is something that most physics teachers skip. A step which is incredibly important to cement the understanding of complex equations, but really often overlooked. And that's asking the question of, does that make sense? In order to understand that, we have to imagine two cubes. First one bumping into the other one. Both of these cubes have their own mass. This cube is traveling at a certain velocity, so it has some sort of momentum. Irrelevant. Now when it hits this cube, it accelerates. And that's where our equation comes in handy. It basically says that the higher the force, the quicker it accelerates. So the more meters it can cover whilst accelerating. The shorter the time for so the more meters it can cover whilst accelerating, the shorter the time for a certain acceleration to occur, and the bigger the mass it can accelerate. That's why all the units are there. Now we understand force, we can get to walk. On understanding walk. So what is walk? Well, walk can be defined as distance we push this cube over. Okay, well, it's not quite the distance itself, it's like the amount of distance the force acted on, so like how far we pushed. So force multiplied by distance, that's walk. So how far we pushed, but pushing is like a essential part. It's force times distance. So imagine a make-it intern pushing a cube. This make-it intern is actively walking, which means that the walk being done is equal to the force of the intern pushing multiplied by the distance the intern is covering. But how does that relate to energy? Well, energy is the capacity for walk, which means that in this case, this is the equation for energy. Kinetic energy of this cube. Now this example is a bit tricky because we have our make-it and then pumping new kinetic energy into our system by pushing the cube. And the cube is losing the energy as thermal energy because of friction, but that's the equation for kinetic energy of the cube. So the work it's doing. Now it's time for the electrical energy equation. What degree do you have, even me? I don't have one. I'm generalist. Make it intern? Yeah, that's what I refer to 3D make-its whenever I insert them in the video. It's basically a model of a make-it, the 3D model. Mickey, yeah, it was woke. That joke doesn't really work when you like put it in quotes, pun intended. Ah, let me take another sip of coffee. Delicious. Okay, electrical energy next. For the electrical energy equation. That's what I said, sharp make it. And so for electrical energy, we're talking about electrons and their movement. So for electrical energy, we're going to start with this. I won't re-explain how to get this equation here because that's a story for another time and another video. So for now, you'll just have to trust me with this equation. Equation which says that the velocity of our electrons is equal to the charge multiplied by the magnitude of the electric field per mass times time. Okay, the point is, if we divide both sides by time, we'll get acceleration equal to this. And if we multiply both sides by mass, we'll get force equal to this. I think you can see where this is going. Back in classical mechanics, we took the force acting upon an object, multiplied by distance, and got the work done. We can do the same thing here, so we can multiply it by the distance and turn this magnitude electric field into voltage. Now we get the energy equal to voltage times charge. What does that mean? Well, imagine a magnet. What this equation says is that the stronger the charge of the magnet, or the stronger the potential acting on it, the more electrical energy it has. That's what happens in our cables, except instead of a magnet we have electrons, so that's electrical energy, not quite magnetism, whole other kind of words. The point is, that's electrical energy. Next, we'd have light energy equations. Come on, make it, you can do it. Stay awake. How difficult is that? Okay. Next we have light energy equations. I can't tell if this video will be longer than the electron one or shorter, honestly. It feels a bit like a Schrodinger's video, or Schrodinger's length. Alright, remember what I said about the radiant energy being related to the wavelength? Why is that? Well, let's go back once again to kinetic energy and its equation of ms squared divided by t squared. Now we can break this equation down into ms divided by t, s divided by t, and we can group those two into E is equal to pv, which means that our kinetic energy is just equal to velocity times momentum, which means that our kinetic energy is just equal to momentum times velocity. Now for electromagnetic radiation, it's a bit tricky, and that's because our velocity is constant. It's the speed of light. So our equation becomes E equals pc. And because of some really difficult to understand relativity / quantum physics, which I just gave up on understanding on the stream and just left it for the wave map video, momentum of photons is just equal to this, where h is the Planck's constant and lambda is the wavelength of the photon. So to recap, we took this equation from classical mechanics and this equation from relativistic quantum mechanics, and ended up with this equation for the energy of the photon. Next up, we'll have... That feels very shaky explanation, actually. I don't say woke for broke. Broke has a very distinct sound to it. You could have gone for walk, as in this. Hi there, Vernon. How you doing? Boy, we're 2 chapters away from being done with the recording. Up, we'll have... That feels very shaky. For thermodynamics, it's really similar to kinetic energy, except this time it's more average. So how could we get that energy? Well, once again, for the 4th time, let's start with E equals ms squared divided by t squared. Now we can take this and reward it to say E is equal to Fs. So energy is equal to the force times the displacement. Now it's time for the ideal gas equation. Now it's time for the ideal gas law equation. So this, PV is equal to nkt, which states that the pressure times volume is equal to the number of particles times the Boltzmann constant times absolute temperature. Now, in order to analyze why this equation could be useful to thermal energy, let's start with the right side, amount of molecules, Boltzmann constant and absolute temperature. In this case, we can just omit the Boltzmann constant because it's not really important. What is important is the N times T, because the absolute temperature basically tells us the average kinetic energy of a particle, and since N tells us the amount of molecules, and since the N tells us the amount of particles, there. Now let's go back to our E is equal to ms squared. Now let's go back to our E equals m squared t squared and define another unit called a Pascal, which is just force per area, which is just P is equal to m1 divided by t squared s. Now we can see that if we take this pressure and multiply it by length, and again by length, and again by length, we get this. So P s cubed is equal to ms squared divided by t squared. Or in other words, ps cubed is equal to the energy. And what is length times length? And what is length times length times length? Well, that's a volume, which means PV is equal to E. And if we merge it with the ideal gas law equation, there. So that's the kinetic energy. So that's the thermal energy. Well, one of them at least. And right here we can already see a certain pattern develop. You see, first we started with classical mechanics and this equation. Then for electrical energy we took this equation and modified it to account for charge with this equation. For radiant energy we did the same thing except with this equation to For radiant energy, we did the same thing except with this equation to account for the lack of mass. For thermal, it's once again the same thing except with this equation to account for the statistical nature of thermodynamics, and there is a reason for it. You see, this equation just tells us the capacity for work in normal everyday objects, like balls or cubes or whatnot. But in the realm of photons or charge or average movement, this isn't enough. Because this is only true for the classical model of physics. That's the thing. If you think about it, work is just a concept. That's it. Nothing more. We made up the concept of work to describe different behaviors of different things. Then we made up the concept of energy to describe how much work something can do. But we can't really simulate all of the atoms in a cube of iron, and the intricate behaviors of the electron clouds, elementary particles, intramolecular forces, intermolecular forces, and so on. And that's why we invent models to simplify things. Of course, nothing is free, so classical model may be simpler than something like simulating everything. Of course, nothing is free, so a classical model may be simpler than simulating everything, but it's less accurate for classical physics. But it's less accurate for classical objects. And if you apply it to something like photons, it breaks down completely. There is no mass. That's why we need to modify it for photons. So that would be the point of this video. Energy is just a concept. Like anything else in physics, different kinds of energy may be treated differently, but they are just capacity to do work. And there is no better example than potential energy. Your voice is so single. You did. Why? How do you do that notation for the equation? You mean this whole thing? This is just equations in Google Doc with LaTeX. So for example, if I want to copy this, it will be C, then rho, if I remember correctly, then it's a fraction of a partial derivative of capital T, partial derivative of T equals to K, fraction of a partial but squared, so up arrow T, well not the up arrow, only the so basically more abstraction. Kind of. In this case, I don't think quite. In this case, it's just inventing a concept. It's not really, well, it's hard to say. It would be a bit misleading called an abstract concept, because this concept can be applied to the simplest of things. This concept doesn't really require complexity, but it is certainly a concept. Okay. Now it's time for the last chapter. So, what is potential energy? Well, if we take a look at kinetic energy, we'll find a pretty straightforward explanation. In physics, the kinetic energy of an object is the form of energy that it possesses due to its motion. Simple as it could be. Then we have this equation as a sort of general equation describing it, which we can modify it for different cases. But then we have potential energy with definition like this. In physics, potential energy is the energy held by an object. In physics, potential energy is the energy held by an object because of its position relative to other objects, stresses within itself, its electric charge, or other factors. Other factors. That's so vague. What other factors? What kinds of factors? Gravity, charge, quantum, nonsense? Well, all of them. For kinetic energy, we do not only have a concrete rigid definition, but also a general equation. But for kinetic energy, we not only have a concrete rigid definition, but also a general equation. But for potential energy, we have this, a function. What is this function equal to? We don't know. In order to describe it fully, you'd have to account for every single thing in this universe which might give you some capacity to do work. Physicists do differentiate between kinetic and potential energy, and there is a solid line between them, but that's only because potential energy is a bit of a misnomer. In reality, it should be kinetic energy for all movement and static energy for everything else. That's because all energy is potential energy. All energy is just potential to do work. All of the things I've described so far and more, like gravity and chemical energy, aren't connected by a solid line. They just all influence each other and That's what existence is. Affecting something, leaving an impact. Light, heat, charge, movement. All of these things are completely different, and yet we use a single term called energy to describe them all. But that's it. To describe them with different models, different equations. We're trying to describe these completely different forces into a single coherent science. And that's what physics is. Physics is the answer to a question of what is energy. Drop mic, honestly. Drop mic on the floor and completely crush it, set it on fire, set it ablaze. Solid. I didn't mean to do that. There we go. Oh, sweet. Everything is recorded. Not gonna lie, never say that again. I agree. I do agree. This time I forgot to notify. Oh wait, did I really forget to notify in the server? Whoops! 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 Did I? Did I do? Okay, yeah, I did. Whoops. That's on me. There. Consider yourself notified. Almost over an hour in. You're notified! Hell yeah! Sick! Cool. There. Perfect. Typical make it behavior. Oh, come on, we all make mistakes. Let's play some music. We're done with the recording segment. My taskbar is broken again. Cool. Hold on. And this. There we go. Is this too loud, too quiet? I feel like it's just right. Neat. It is good music. Okay, now in order to jazz it up a bit, and in this case by it I mean the recording, I'm gonna do a vocal enhancer on these suckers. There we go. And there, it's all recorded. Cool, cool, neat, fun, festive. Lovely. Now the only thing left is to like edit it all and just finish all the animations and like, you know, just generally just like... Why is this such a long video? I was honestly expecting it to be 10 minutes long. So it's gonna be around 26 minutes, although I might add like an ad segment at the end, so we could actually reach 30. It's a possibility. It's not impossible. Depending on how many minutes we waste in the actual recordings. Now, I'm pretty certain we do have... Oh, these are all my thumbnails for the stream, is not what I'm looking for. I don't want to spoil any other videos, so I'll have to traverse this quietly. Hold on. Intro frames. This, correct? Wait, why did I do it without the... Oh, did I already have a recording? I must have had the recording. There's no way I would do an intro without having a recording. I refuse to believe. Audio for intro. Would you look at that?
Heat. Temperature. We all know what they are, right? I mean, when you touch something and it burns, when you heat up a metal and it...
Did I not render the entire intro? Oh no, I did. It's just that the rest of them don't have freaking name. Okay, it's fine. I'm gonna do it. I'm gonna fix it. Give me a second. Yeah, I always forget how to do loops in Bash. No, wait, not Bash. Loops in PowerShell. Rename was the function, correct? No? Rename? No, damn it. Renaming and also renaming a file in... Oh, was it rename file? I think it might have been rename file. Are you aware that we can't see the screen? Now you can. I have been locked out. Oh, you. Rename item. That's such a dumb name. I don't like it. All of these are missing and, you know, PNG at the end. Festive. So what we're gonna do is we're gonna do loops in PowerShell. Yeah, just give me a sec. Like, can I has an example? I can has an example. How sweet of you. Wait, hold on. Rename item, not time, item. Rename item 171 to 171.png. I beg to differ. It's right there, in fact. 0 at the end. Oh, come on. You suck. There we go. It works. Sick. So now all we need to do is just for zero point 666. Oh no. Not bound val. There we go. 666 and then rename item. Was it val? I think PowerShell was. Oh no, this is 0. Okay, I think PowerShell was this simple, correct? Quick fix to a quick problem. Okay, let me re-import it then.
Heat. Temperature. We all know what they are, right? I mean, when you touch something and it burns, when you heat up a metal and it shines, when you heat up a semiconductor and its conductivity increases, except... why? Like, why do all of these things actually happen? And what the heck do these equations even mean?
Oh, I forgot that these equations are relevant. Oh no. Oh no.
Well, surprisingly, there's a simple-ish reason for all of them, and that reason is...
I kind of forgot we sort of might have kind of almost like redid the intro. Teh. Whoops. Into the dumpster it goes. So, the new intro, what does it look like? Light, heat, charge movements. All these things can be different. We're seeing things called energy to describe it all. Why is that? You're gonna need this recording.
Clearly walking. Charge. Movement. All these things are light, heat, charge, movement. All these things are completely different, and yet we use a single term called energy to describe them all. Why is that? Why would they be connected at all? And most importantly, what even is energy?
I might start it. Oh, no, wait, it don't start. Oh. I always forget what music I start the video with usually. I do remember I have one. I just always pick the same one. Oh no, hold on, what just happened? Give me a second. No space on the memory card. No space. Card sick. Oh, okay.
Light, heat, charge, movement. All these things are completely different, and yet we use a single term called energy to describe them.
Ah, this is gonna be painful. For intro. I have to remake the whole intro animation. Not MP4, only MP3.
Light, heat.
Oh boy, why am I so tired? Oh yeah, I haven't slept. That's right. The bang room slaps. Yeah, it's great. It's made by I saw the KC Music on YouTube. I would recommend checking him out. It's Soda KC. And here, Kwant! Oh my goodness, I haven't seen you in such a long time. Hi, Kwant, hi! Why is it so hot in this room? Oh yeah, because I am here. Almost 20k subs, I just realized. Yeah, we're really close. Really close. Like 2 or 3 more days. And then we're gonna be at 20k. If it keeps going like it's going. It might just stop. Possibility. Stream like 1 AM, otherwise I want to play. I play is oh my goodness, insane game. It's great! Actually, it's really good that you didn't watch the stream then, because it would actually spoil everything. We should play something though. I am feeling a bit weathered down at this point. Hold on. Weathered down and a bit tired, so I'm gonna need to rest up. I do know. Oh wait, you're still going. That makes sense actually. Being in one, that does make sense. For some reason, my mind just assumed that you mean played by played. You mean finished. I don't know why I assumed that. want this. There we go. Hold on, I just had to set something up. So should we play something? Very slightly remember the end of the game. Oh, yeah. Depends on how late. When goes the ending, it shouldn't matter much. Second driving and everything in general. I can't relate. I'm the best spaceship in I'm best spaceship, just the best spaceship in general. I'm great at I'm a great spaceship. Should we play some GTFO? I do feel like a bit of GTFO right now, honestly. I always forget just how awful that game is, and always just start with sort of feeling of childish wonder. We're like, oh yeah, this time I'm definitely gonna beat the first level, and I just end up dying. Because of course I do. Yeah, this game is basically not pleasant for the eyes, or ears, or in general not pleasant. I'm probably just gonna try one, because I wanna get asleep a bit. R1. Not completed, yeah. Yeah. Not completed, indeed. Heavy assault rifle, I do believe that's... Drekka is good, I like the Drekka. A bit. Wait, change loadout. What else do we have? Best entry. Tempting. Also kind of tempting. Low damage by over-penetrating rounds. Staggering effect. Well, I do like staggering effects. Well, sucks to suck, I guess. Is this finals? Yes, it is the finals. It's the hit game Among Us, and I'm the imposter, and I have to impose over all of the crew. I'm the imposter, he said, and then he imposed it over all of the crewmates. Hold on, we're looking for crewmates. So what is that red thing up the bottom right corner? Just flashed, cool. Nothing. Neat. Long range flashlight. Hell yeah. Okay, this is actually almost decent. Almost pretty great actually, even I would say. Another long range flashlight. Hell yeah. There are the crewmates. So what was that glitch? Jonathan, thank you so much for... I don't know that currency, but thank you so much for 37 of it. Let's celebrate. Thank you so much. Have a burger for troubles. Thank you. I will. I will enjoy a burger. Oh damn it! Now I. Whenever someone donates on stream, I always feel bad because I know I'm not entertaining enough. I don't even know how to react. Thank you so much. That's it. Let's keep going. Oh no, that's not it. That's not it. One bit. How did you not react the first time? It doesn't matter. Thank you. That offsets the entire awfulness of this game. Okay, what if I wake the sleeper? Hypothetically. I guess it doesn't matter. They're just blind. Okay, so the thing is... Oh, medkit. Oh, that's great. If only I didn't waste so much health already. I did waste a lot of health. Ooh, great. Great, and getting better by the second. This might be already a pre-solid win. Long range flashlight, hell yeah. Oh yeah, I already left it because I have a mine, that's fair. Okay, well, I suppose this is about as good of a scenario as any to test out the new sentry, since we got the mine, which is pretty lucky. We lost a bit of health, which is pretty unlucky. Oh well, can't win them all. Another crate. My goodness, I am just drowning in loot. Oh, suck it. Suck it. Dead? I'll make sure. Okay. Great. Good. I lost health, but... Oh well, happens. Seafoam grenade. Oh, I don't know if I actually want to use it at this point, because it's really good item. Oh boy, it's a good item. Okay, we'll try to do it without the seafoam grenade. I'll try to greet this, because of course I am. This sentry right here. Rounds remaining. That's a okay, that's quite fun. PHP sounds relatively cheap. I still thank you. Make it collecting. What do you mean? You mean not walking? Yeah, yeah. It's a new policy. Recording down, yes. It's a new policy. After each walking stream, we're gonna play a single round of GTFO. Just to, like, eventually get it. Oh my goodness, I should have used the goop grenade. I should have used the goop grenade so bad. Okay, so the shotgun is better. Fudge. Seafoam launcher is also there. Good for door reinforcement. I'll die without a turret. Or will I? Yes, I will. Or will I? Yes, I will. Never played the game. It's pretty famous for being difficult, and difficult as a group and borderline impossible when you're playing alone. And I'm playing alone. You know what? Let me actually. I'm curious. GTFO solo run. But emotional support. Thank you. Emotional support is all I need. Wait, hold on. What now? You can slide in this game? So they recommend a mine deployer. Alright. I guess I'm gonna pick a shotgun then. What's this game and what's the main goal? The main goal is to depend on the level, and this game is GTFO. Alright, this is the last one though, and I'm gonna end the stream, I'm gonna go to bed because I'm tired. The idea is, right here is the first level, which I still haven't beaten, and we have to extract something out of the facility. And then once we extract it, then we win. It's simple. One last game. Okay, no, this time I'm honest. Honesty, one last game. We can deploy mines now, but we don't have a turret. I do feel like having a turret could be convenient. Now all I have to do is not screw it up. We start with 2 chests. That's really good. Glow sticks, my favorite. Can they hear messed up hacks? Well, I guess we'll find out. Or we won't, because I'm such a good hacker. Oh, great. Splendid. We got some ammo for the mine deployer. I believe in you. You really shouldn't. Like, even my overestimating of skill isn't enough to justify these attempts. The attempts themselves. I'm not even talking about like hoping to win or something, because that's obviously beyond. And mine! I have a deployer. I don't really need a mine. But I'll take it. I'll take anything at this point. I don't see anything. That's counterintuitively usually a bad sign. They're not spawning here. They must be spawning somewhere, right? If they're spawning somewhere, not here. Where are they spawning? 2 crates. That's good. With a glow stick and a medi. I do like a medipack. 7. I'm gonna wait. You should play Call of Duty. Maybe, I don't know. Alright. Give me this. Open it up. Where are they? I haven't seen a single one. Dead. Okay, I hear what. There it is. Still, there's suspiciously few of them. There was a couple in this room, but that's doesn't feel like enough. Shut up. Stay in the corner and crouch. There's one over there. There. Finished. What else do we have? Glow sticks. And you both here on the slice of pie. I would recommend slice of pie more. It's not really, you're not really donating on the website. You're more like donating charities. Website is just there to keep a record, to like keep a public record of donations. It's basically made to give everyone bragging rights for their donations. Like, what kind of music do you like? All of it. And I do mean the all of it. From Taylor Swift through No Cock Like Horse Cock to Used to Darkness, Shut Up, Smile Like You Mean It, Deadman's Poison, Stop, Bad Mutant, or whatever you are. Okay, so the basic idea, if I'm understanding this correctly, is you take this, which is a mine thing, you set up a mine, then you set up a mine, then you use up the refill pack to refill your mines, and then that's it, and we just win. Wide close. I think that's it. I have to be careful to not walk into a mine though. Chinese number up, all of it. I haven't heard of music which I would actively dislike yet. Fentanyl too, why not? Must I get the money? That's fair. I also don't want to pressure people, especially in donating me. In fact, I actively discourage donating to me. I consider that. Oh, whoa, that worked. That worked surprisingly well. Oh, you'll suck. This shotgun is outstanding. Why not been using it before? What am I dying to? You, okay, you're still alive, clearly. You're very clearly alive and kicking. Okay, weekend? Yeah, weekend too. Alright, shotgun is definitely a weapon to keep. Anyhow, as I promised, I'm gonna go now to sleep because I'm just tired, and when I'm tired, I'm not productive. And I'm not productive, then what's the point of being awake? Anyhow, last game? No, we're not falling in that rabbit hole. Anyhow, for now, that'll be it. Thank you everyone so much for watching, and thank you so much, Jonathan, for the donation, and have a great day. Bye.